America looked at the challenge of powering a 60-ton battle tank and put a jet engine in it. Germany looked at the same challenge and answered with 47.6 liters of diesel. France looked at both answers and decided neither was good enough. So they built something the world had never seen before, an engine that is a diesel, but also a gas turbine at the same time. This is the SACM V8X-1500 Hyperbar, and it is unlike anything else on a battlefield. To understand why France built this engine, you have to understand what they were driving before it. The AMX-30 was France's main battle tank through the Cold War. It was fast, it was light, and by the early 1970s, it was already becoming obsolete. France knew they needed something new, and in 1980, they signed a joint development agreement with West Germany. In France, the program was called Napoleon I. In Germany, Kampfpanzer III. But there was a fundamental problem from the very start. Germany had already developed the Leopard 2. It had entered service just 1 year earlier in 1979. As far as the Germans were concerned, they already had an excellent tank. So Germany's proposal was straightforward. Take the existing Leopard 2 chassis and build a new turret on top of it. France rejected that immediately. The French had spent years developing a completely new chassis with advanced technology. They had no intention of abandoning that work to build on top of a German design. Two nations, two completely different starting points, and no common ground between them. By December 1982, the program was dead. The Kampfpanzer III never became a tank. Germany continued refining the Leopard 2. And France walked away to build something entirely on their own terms. The result was the Leclerc. And at the heart of the Leclerc was an engine philosophy that no other production main battle tank would ultimately adopt. If you've seen our videos on the M1 Abrams and the Leopard 2, you know the trade-offs. The AGT 1500 gas turbine in the Abrams is a masterpiece of aerospace engineering. Instant, smooth power. Cold start capability at -22 degrees Fahrenheit. But it burns fuel at a staggering rate, and it burns even more just standing still. The MTU MB873 in the Leopard 2 is the opposite. 47.6 liters of raw diesel engineering. Efficient, reliable, with enormous torque. But in extreme cold, a diesel that size needs time, a lot of time, before it can move. France saw both solutions and identified a gap. What if you could have diesel efficiency, but without the turbo lag? What if you could have turbine-like power delivery, but without the fuel consumption? That question is what produced the Hyperbar. The name Hyperbar comes from the boost pressure. And when you hear the number, you'll understand why they needed a new word for it. A standard turbocharged car engine, even a high-performance one, operates at around 1 to 2 bar of boost pressure. The Hyperbar system runs at 7.5 bar. That is not a typo. To put it in perspective, the mean effective pressure inside the V8X engine is 32.1 bar. The largest diesel engine in the world, the Wärtsilä RTA96, used in cargo ships, achieves a mean effective pressure of 18.6 bar. A tank engine produces higher combustion pressure than a ship engine. So how does it achieve this? A conventional turbocharger uses exhaust gases to spin a compressor that forces air into the engine. The limitation is physics. At low RPM, there's not enough exhaust gas to create serious boost. That's what causes turbo lag in most diesel engines. You push the throttle. You wait. Then the power arrives. The Hyperbar system eliminates that problem with an elegant solution. Alongside the diesel engine sits a small Turbomeca TM307B gas turbine. Not as a main power source. Not as a spare engine. But as a high-pressure turbocharger, one that generates its own power independently of engine speed. This turbine feeds compressed air into the diesel at extreme pressure, even at idle. There is no waiting. There is no lag. The moment you accelerate, full boost is available. Think of it like this. In a normal turbocharged car, the turbo is a passenger. It works when the engine tells it to. In the Hyperbar, the gas turbine is a partner. It works continuously regardless of what the diesel is doing. And when the main diesel engine is shut down entirely, that same gas turbine continues to run. powering all electrical systems, the fire control system, communications, and sensors. No external power unit needed. The turbine handles everything. So what does all of this produce? The V8X-1500 is an 8-cylinder, V8 configuration diesel. 1,500 horsepower at 2,500 RPM. And torque, 3,576 lb-ft at 1,700 RPM. Now remember from our Leopard 2 video, the MTU MB873 makes approximately 3,465 lb-ft of torque. From a V12 with 47.6 liters of displacement, the V8X makes more torque. From a V8 with significantly less displacement. That is what 7.5 bar of boost pressure does. The Leclerc itself weighs around 56 tons. Noticeably lighter than either the Abrams at 63 tons or the Leopard 2 at approximately 62 tons. Combined with that power output, the Leclerc achieves a power-to-weight ratio of 27 horsepower per ton, the best of any Western main battle tank. The result, from a standstill, the Leclerc reaches 20 miles per hour in 5 seconds. Top speed on road, 45 miles per hour. Cross-country, around 34 miles per hour. And range, on internal tanks alone, approximately 342 miles. With external tanks fitted, that extends to around 404 miles. Compare that to the Abrams at roughly 250 miles on internal fuel. The Leclerc travels significantly further on the same amount of diesel. There is one advantage of the Hyperbar system that rarely gets mentioned. On a modern battlefield, thermal imaging is everywhere. Enemy infantry, attack helicopters, drones, they all look for heat signatures. The M1 Abrams gas turbine blasts exhaust gases at up to 1,300 degrees Fahrenheit. Its thermal signature is enormous. You can see an Abrams on thermal imaging from a significant distance, even when it's trying to hide. The MTU MB873 in the Leopard 2 is better, but a 47.6-liter diesel still generates considerable heat. The Leclerc's Hyperbar system operates differently. Because the gas turbine burns fuel more completely and efficiently, the exhaust temperature of the TM307B never exceeds 370 degrees Fahrenheit, regardless of engine speed. Additionally, the Hyperbar produces no visible exhaust smoke during acceleration. None, under normal operation. That means on a battlefield, the Leclerc is significantly harder to detect by thermal sensors than either of its rivals. In modern warfare, where drones and precision munitions make visibility a death sentence, that is not a minor advantage. There is something important we need to address before we talk about the UAE. In our Abrams and Leopard 2 videos, we talked about the power pack swap, the ability to pull an entire engine and transmission as a single unit and replace it in roughly 30 minutes. The Leclerc is also designed as a modular power pack. It can be replaced in the field. But here is where honesty matters. No publicly verified swap time exists for the Leclerc the way it does for the Abrams and Leopard 2. And that silence tells you something. Because the real challenge with the Hyperbar is not pulling the power pack out. It is what happens next. When you service a conventional diesel, you need diesel mechanics. When you service the Abrams turbine, you need gas turbine specialists. When you service the Hyperbar, you need both. At the same time. The gas turbine inside the Hyperbar, the Turbomeca TM307B, runs continuously at extreme speed and temperature. It is a high-precision aerospace component. It tolerates no improvisation. And as the Leclerc ages, the parts for that turbine become harder to source. In 2020, France's own parliament flagged that sustaining the industrial supply chain for the TM307B needed an additional €4 million just to keep operating. That is not a mechanical problem. That is a strategic vulnerability. Leclerc units have consistently reported higher maintenance hours per operating hour than either the Leopard 2 or the Abrams. The Hyperbar is brilliant engineering. But brilliance in engineering and simplicity in the field rarely coexist. And now for the part of this story that directly connects all three of our videos. When France sold the Leclerc to the United Arab Emirates, 388 tanks, one of the largest export deals in French military history, the UAE had a specific request. they didn't want the Hyperbar engine. Instead, the UAE Leclerc was fitted with the MTU MT883, a German-built V12 diesel from the same MTU Friedrichshafen family that developed the engine powering the Leopard 2. Related by engineering DNA, but a different and more compact unit, developed specifically for export applications. Think about that for a moment. France's most advanced tank, running Germany's engine. The reasons were partly political. The UAE had financial interests in MTU Friedrichshafen. But partly practical. The MTU engine required less specialized maintenance than the Hyperbar system, which demanded highly trained technicians to service the gas turbine component. This is the tension at the heart of the Hyperbar. It is a brilliant, unique, world-class engineering achievement. But it is also complex. More complex than a standard diesel. More complex than even the Abrams turbine in some respects. And complexity in the field is always a liability. So after 3 videos, 3 different nations, 3 completely different engineering philosophies, where does the Leclerc's V8X fit? The AGT 1500 in the Abrams is the power statement. Aerospace technology, multi-fuel, instant cold start. But it drinks fuel at a rate that challenges logistics on every operation. The MTU MB873 in the Leopard 2 is the endurance statement. Proven, reliable, efficient, easy to swap in the field. But in extreme cold, that 47.6-liter block needs time before it can move. The V8X Hyperbar is the French compromise, taken to its logical extreme. Diesel efficiency, turbine response, a thermal signature lower than both rivals. The best power-to-weight ratio in the West, and a range that outperforms both. But it comes at a cost. The engine is complex. Maintenance requires specialized knowledge. The gas turbine component has faced obsolescence challenges. In 2020, France's own parliament flagged that sustaining the industrial chain for the TM307B turbine needed significant additional funding. It is perhaps too clever for its own good. America chose raw power. Germany chose proven endurance. France chose engineering brilliance. All 3 answers have merit. And all 3 answers have a price. 3 nations. 3 tanks. 3 completely different answers to the same question. If you haven't seen our breakdowns of the M1 Abrams AGT 1500 and the Leopard 2 MTU MB873, they're linked right here. Thanks for watching. I'll see you in the next one.